In my last video, LOPs for solo artists, I covered two of the various composition arcs available in USD, namely sublayers and references. In this video, we'll go over a few more of them in the context of creating a fully featured USD component asset. We'll start by creating a simple one-file component consisting of a mesh and a material, then we'll add proxy and render purposes for viewport performance. Next, we'll cover how to split our asset into multiple layers, the various USD file formats and extensions, and using output processes to export all of our files and textures to the same location. Then we'll cover most of the composition arcs we missed. Payloads, for selectively loading and unloading scene elements, variant sets, for switching between scene variants, and inherits, for broadcasting overrides to scene elements. And then after all of that, we'll look at importing our asset into the layout asset gallery. Before we start, it's important to point out that Houdini comes built in with the component builder LOPs, which do an excellent job of simplifying the process of making feature-rich components. These set up purposes, variants, payloading, class inheritance, and even asset thumbnails for you. But that's exactly why we won't be using them. If you don't already know what those things are, and whether or not you need them, then it can feel quite overcomplicated for what should be a straightforward process of saving an asset to a file. So we're going to build a component from the ground up, so that we can learn what each of these features are for, and how to implement them. That way you can decide for yourself which features are important for your workflow. Let's start our simple component. I'm going to use this basil asset from the Grasswold plant library, which you can find at gscatter.com. So I'll put down a SOP create, call it basil_big, and dive in. With a file SOP, if we take a look at the basil directory, we have an FBX file for each level of detail model. For now, let's just pull in LOD0. The model is huge, so I'll start by bringing it into meter space with a transform set to a uniform scale of 0.01. You can see we have lots of overlapping models. In the geometry spreadsheet, we have a name attribute separating each one. For now, we only want one, so in the viewport, I'll select the first named piece, delete it, and then set the blast to delete non-selected. We've also got a bunch of attributes we don't need, so I'll put down an attribute delete and delete everything except normals, UVs, and name. Jumping back up to the stage, we have our basil component with a mesh underneath. Let's add a material. Put down a material library, and then dive in and create a USD material X builder and dive into that. We'll need an image node for each texture. Let's start with albedo, and I'll just grab the smallest resolution for now. Plug that into base color, and then we'll copy it to pull in roughness, then plug that into specular roughness, and set its type to float. Copy it again for translucency, which will be a color, and plug that into subsurface color. Then copy it one more time for normals, which will be a vector 3. And for this one, we need to plug it into a Material X normal map node before plugging that into normals. Let's jump up to the stage, click autofill, assign it, and see how it renders. I'll add some light to help with things. The albedo seems to be working fine, but we have no translucency, so let's fix that. Translucency is controlled by the subsurface. So on the standard surface node, set the subsurface to 0.5 and geometry to thin walls so that the light can shine through the leaves. The reason we don't set the subsurface to 1 is that then we lose a lot of the albedo, but we can boost the color of the translucency a bit by adding the albedo back into it. I'd like a bit more definition in the normals, so on the normal map node, I'll bump that up a bit. 10 is too much, so maybe 4. And lastly, I'd like the leaves to be a bit shinier, so I'll tweak the gamma on the roughness with a range node. Around 0.7 looks good, and I'll drop the specular down a little as well. And that's a good looking basil plant. Before we export it, we need to make sure that the material is under the component prim, otherwise it won't reference back in properly. So on the material library, we'll change the material path prefix to /basil_big/mtl/. Now we can save that to disk with a USD ROP, and we have a nice little basil asset we can reference into scenes. I'll set the export path to $hip/USD/basil_big/basil_big.usd. It's also a good idea to explicitly set the default primitive in a USD file. We can either do that with a configure layer LOP, or in the USD ROP under the layer metadata, set it to /basil_big. I don't want to export the lights though, so I'll disconnect those from the ROP. Great, let's move on to optimizing the viewport performance of this asset by setting purposes. In USD, purpose is mainly used to allow you to have a lighter proxy geometry displayed in the viewport and only show the full heavier geometry at render time, keeping the viewport more interactive. Inside the SOP create, we can make the proxy geometry with a polyreduce. With a name SOP, we'll replace LOD0 with proxy, and merge that with the LOD0 mesh. Then on the blast, just put an asterisk in place of LOD0. That way we'll blast everything except the first variation of the LOD0 and proxy meshes. And I'll add an output node to make sure that we're always outputting from the end of the chain. Back up at the stage, we now have 2 meshes under our component. I'll move one to the side so we can see them clearer. In the scene graph tree, under the settings button, we can add purpose to the display, which shows that the meshes are set to default. This means that they'll both show up in the viewport and in the render. We can change this with configure primitive LOPs. I'll set the proxy mesh to proxy, then duplicate it, and set LOD0 to render. The viewport can get a bit stuck when you change purposes, so you can give it a kick by deleting some nodes and hitting undo. Now the LOD0 mesh has disappeared, but if we render, then the proxy mesh disappears instead. If you click the sunglasses icon to the right of the viewport, you can choose which purposes to display. Guide is an optional purpose used by Houdini for the layout physics tools, so I'm going to ignore that for this asset. We have our purposes set up, but having the meshes together in the root of the component isn't very organized. Just like we have our material in the material scope down here, it's a good idea to have geo under its own scope, and then separate scopes for the purposes under that. I've already covered how to do this in SOPs in my building components in SOPs video, so here I'll show you how it's done in LOPs. After the SOP create, add a restructure scene graph. By default, this will reparent primitives. So point it to the LOD0 mesh, and then set the new parent to /basil_big/geo/render, which will create geo and render scopes, and parent LOD0 underneath. Next, duplicate the restructure, point it to the proxy mesh, and set the parent to /basil_big/geo/proxy. Now we can relink our purposes to the proxy and render scopes. And that's our purposes all set up. Annoyingly, you can see in the scene graph tree that the reparenting has changed our component from an XForm to a scope. This is a bug that should hopefully be fixed in future versions beyond 20.5.584. If we leave it like that, it means our component can't be transformed, which wouldn't be very useful. So we'll fix it with another configure primitive, setting the schema type to XForm. Now let's take a look at splitting our component into separate layers. While having everything in one layer feels neat and compact, there are good reasons to split things apart. So here's the plan. We'll split the geo and materials off into their own layers, and reference those into an asset layer. This allows you to make changes to individual parts of your asset without necessarily having to resave the whole thing, which is especially useful for heavy geometry. It also allows for easier reuse. For example, if you want to reuse an asset's material or mesh elsewhere. Let's start with the geometry layer. Put down a configure layer LOP, call it geo_layer, and set the save path to geo.usdc, and the default primitive to /basil_big. I'll also set the axis and scale. This information is useful to have for reference if the model needs to be pulled into another DCC. Next, I'll split the material library into its own branch under a layer break. This way we only author the material and its assignment. Then add another configure layer LOP, this time setting the save path to mtl.usdc, and set the default primitive on this one to /basil_big as well. Then with a reference LOP, we'll connect those two layers to the multi-input to reference them into the asset layer onto /basil_big. In the scene graph tree, the component prim is now green to show that it has a composition arc being applied. And optionally, we can also put down another configure layer to set the default prim, axis and scale for this main asset layer as well. Before we export, now would be a good time to quickly cover USD file formats. USD currently has a few options for how to store USD data. USD crate files are binary files. They have a much smaller file size and are much more memory efficient, making them great for geometry or any file with a ton of data. USD ASCII files are simply text files, so they can be easily read and edited with any text editor. This is really handy, but it does mean that they're much less space and memory efficient, so they're best saved for debugging or for light data, like USD files that are simply composing together other heavier USD files. There's also the USD zip format, which you can think of as a zipped folder of USD and texture files acting as a single USD file. These are called packages and are used mainly in real-time applications. We can specify which format to use by setting the file extension to USDC for crate files, USDA for ASCII files, and USDZ for zip packages. The USD extension can be crate or ASCII. It's a good idea to use this generic extension for asset layers, as that way if you need to change the format later on, it won't break any references to the asset. By default, Houdini will save .usd files as crates, but you can specify ASCII by adding this SDF format args string to the end of the file path, and setting the format to USDA. With that done on a USD ROP, let's hit export. If we look in the asset folder, it looks like we've only saved a single layer. Why is that? Let's sublayer it in and take a look. Everything looks fine. However, if we inspect the layer contents, it says that the geo and material layers are being referenced from a user folder. And if I take a look, there they are. Houdini saved them here because on our configure layer nodes, we only set the name of each layer, not the path. I don't want to have to manually set paths for different layers though. This is Houdini. We don't do that here. The solution for this is to use output processors. On the USD ROP, under Output Processes, there should be one applied by default called Use Relative Paths. This takes all paths to USD assets and makes them relative to the main USD layer on export. If we add Save Paths to Relative Output Path, and then export again, our layers will now all correctly save to the same output directory. We can even go a step further and save the texture files in here too. Going back to the USD ROP, we can add another output processor called Copy All Assets to Referencing Layer directory. This will find all non-USD assets like texture files and VDBs and copy them into a subfolder of our export folder. I'll call the folder text, as it'll store our texture files. The output processes are run in the order listed here. So if we export now, it will make all paths relative, then copy the textures. We needed to copy the textures first, so that when the paths are made relative, they correctly point to the new location in the text folder. We can do that by clicking on these arrows here to put the Copy Assets processor first. Now export again, and our textures will show up alongside the USD files. And if we inspect the paths, we can see that the main component layer is indeed pointing to the geo and material layers using relative paths. And the material layer is pointing to the new texture location using relative paths. Perfect. With that set up, let's take a look at payloads. Payloads are a composition arc that's basically a reference that you can choose not to load. Imagine trying to load a really heavy scene with hundreds or thousands of assets just so you can address some feedback on the position of a single element. No need to imagine, we can do it right now. But first I'll make sure to switch back to proxy geo in the viewport. Here I'm loading the ALAB reference scene from Animal Logic. We can't see much because of the scene scale, so I'll adjust my clipping planes in the viewport options. Now, despite loading close to 50,000 primitives, the viewport is still amazingly interactive due to the lightweight proxy geometry, but it still took a little while to load everything. It's especially heavy if we want to evaluate the render geometry. Turning that on takes a fair while to load, and drops our viewport performance by at least half. If I just want to focus on a small section, then it's overkill to be loading the whole scene like this. If I turn off payloads on the sublayer, the scene loads super quickly and should display bounding boxes for all of the components. If it doesn't, then you can force it by clicking on one of these dots under L a couple of times to toggle the payloading on and off. The bounding box information is likely behind a payload that we haven't loaded yet, and so doing this forces it to load. And now we get this little square barrel icon to indicate that there are unloaded payloads. And now I can selectively load and unload assets in the scene. You can control the loading of payloads in a number of places. A configure stage set to set primitives to load will make all payloads unloaded by default for the whole scene. For more local control, sublayer nodes can choose not to load payloads under them. And in the scene graph tree, there's this mask button that has an option to unload payloads in the viewport, but keep them loaded in the tree, which is handy for navigating all of the prims that are in your scene without having to load all of the geometry to display them. Now, if you're a motion designer and your scenes don't typically contain hundreds or thousands of unique assets, then this might not be something you need to worry about. That said, it's great to have the flexibility in case you do need it, so let's look at how to set it up. After the reference, put down another configure layer, set the save path to payload.usdc, and set the default primitive to our component. After that, put down another reference, and again connect it via the multi-input, and set the path to /basil_big. This time, we'll set the reference type to payload input. In the scene graph tree, the component has now turned orange, indicating that it's behind a payload. If we take a look in the layer panel, you can see that our main asset layer now only contains a definition for the prim, which is payloading our payload layer. There's not enough information in here at the moment, so if we were to save this as is, we'll run into a couple of issues when the payload isn't loaded. To demonstrate, I'll put down a configure stage, and under Load Primitives, select Set Primitives to Load. Our component has disappeared because the payload isn't loaded. That's good, but we don't have a bounding box, and if you look at the scene graph tree, our component isn't a component or an X-form anymore, meaning it can't be transformed. Fixing both of these issues is as simple as adding a loft payload info node. We now have a bounding box, and the asset is back to being an X-form component. As you can see in the layer panel, the loft has grabbed the schema, kind, and extents hints from the composed loaded asset and copied them into the asset layer. That way, when the payload is unloaded, we can still display the bounding box and transform the component. With that set up, let's look at creating variants. A variant set is essentially a switch that allows for changing between various states of the scene graph tree. Each of these switches is called a variant set, and each state is a variant. I'll use the pighead to demonstrate. Under the Variants tab, you can see there are two variant sets defined, one for geo and one for materials. If I change the variant name for the geo set, we switch between different states of the pig mesh. In the material set, there's only one variant defined called default. However, we also have the option for no variant, which will turn off the material assignment. Variant sets don't simply have to be geo or material switches. They can contain any kind of USD scene data you like. Going back to our component, let's add a variant set to switch between LODs. There is a lot for this called create LOD, which will set up the variant set for you, and uses a polyreduce to create the variants. But in our case, we already have LODs saved as FBX files, so we'll use those and set up the variant set ourselves. Before we get into it, I'll just disconnect the geo nodes from the network for now, so we can focus on what we're doing. We'll start by grabbing the LODs we need. In the SOP create, copy the file SOP a couple of times and point them to LOD1 and LOD2, then merge them in with LOD0 and our proxy. And then move this transform after the merge so everything gets transformed into the correct space together. Back up at the stage, we now have 3 LOD meshes and the proxy mesh. The new LODs aren't being parented into the render scope, but that's okay because we're going to change the approach a bit. Instead of making the restructure from our SOP create, we'll instead define the structure up front and graft the meshes into place. So let's do that. Put down a primitive LOP and call it component. I'll set the path to /basil_big and make it a component kind. Append another primitive, call it scopes, and in the paths, add /basil_big /geo/render and /basil_big /geo/proxy. Then set both primitive type and parent primitive type to scope. Now we can connect that to the nodes where we set the purpose, and we can delete these restructures and configure as we don't need them anymore. Since LODs are all essentially the same shape, we can use the same proxy mesh for all 3. So rather than redefine it for each variant, we'll just add it in now with a graph branches node. Set the path to /basil_big /geo/proxy, then point the source prim path to the proxy mesh. We can't see anything because our viewport still has proxy purpose turned off. So let's turn that back on for now. Proxy mesh is in the right place in the tree, but I want it to be named like it was before. So in the destination path, set it to /basil_big. That's added an extra X form, so uncheck treat destination paths as parents to remove it. And lastly, this has turned the proxy scope into an X form. So we'll fix that by setting the parent primitive type to none and the primitive specifier to over. So now we've copied the proxy mesh into place without affecting the rest of our structure. With that done, we can create our variant set, which is done with the add variant LOP. There are 2 options, add variant to existing primitive and add variant to new primitive. Ultimately, these both do the same thing. The existing primitive one just creates this context block, which performs a layer break to help strip out data you don't need in the variant. So we'll use that one for now. Connect the graph proxy to the first input of the add variant node, as well as the begin variant block. Set the primitive path to /basil_big. That will be the primitive that holds the variant set. And I'll call the variant set LOD. Before we move on, let's take a quick look at the layers panel to see what the node is doing. In the first input, we define the structure of the component, as well as the proxy mesh. The add variant LOP is prepending the variant set we named LOD, and is setting the current variant, which by default is named after the node that's connected to it. We can toggle the set variant selection parameter to remove this if we don't want to set a variant yet. I'll just leave it on though. I don't like the default variant name, so I'll set it to LOD_ and then @input -1 in backticks. So the first variant is now named LOD0, which is much nicer. If we scroll down past the proxy mesh definition, we see where the variants are defined. We have an empty LOD0, and if I add another connection, another empty variant is added. If I add a sphere on that input anywhere under our component, we see it show up under LOD1. And now if I right-click in the viewport, we can select a LOD variant, which will add a set variant node for us. And as we change between variants, we see the sphere appearing and disappearing in the viewport and the seed graph tree. So you can think of setting a variant as switching between which of these branches will be sublayered over the component. We don't want a sphere though, so let's delete that branch and get our first LOD mesh into place. We'll graft them in just like the proxy mesh. So copy the graph proxy node, change the path to the render scope, and the source prim path to the LOD0 mesh. I'll disable the proxy purpose in the viewport again so we can see more clearly. And if we select the variant node, we now have the LOD0 mesh being defined under the variant name LOD0. Perfect. Let's duplicate the graft for LOD1, and again for LOD2. Hook them up, and now with the set variant, we can switch between LODs. Perfect. Well, almost. This manual approach to making variants is fine, but since we're just iterating through the LOD numbers, we can make it a lot cleaner in this case by using a for each loop. The for each has 3 inputs. The first is the stage input, so we can connect the graph proxy there. The third input is for iteration, so we can connect the add variant here. We can ignore the second input for now. That's an optional input for feeding things in to iterate over. Now let's take the for each begin and put it above the variant block. The orange context block is quite big and is indicating that all of these nodes are caught up in the loop. This is because we're piping our component structure into the add variant and then into the iteration port. So each iteration will contain the whole component structure. We don't want this, so let's disconnect the graph proxy from the add variant. We're also currently adding 3 variants each loop, so we can delete these 2 graphs. And these 2 blocks are just performing a layer break, so we can delete the variant block as it's redundant. And since we've deleted that, on the add variant node, we can uncheck create options block. For future reference, we've essentially converted the add variant to existing primitive setup into the add variant to new primitive version. Since we only have one variant input, we'll need to change how we set the variant name. On the for each end, you can see the iteration variable names. For clarity, and so we can nest this loop later, we'll rename these to LOD iteration, LOD num iterations, and LOD iteration value. So now we can use the variable LOD iteration to get the current LOD number. Let's put that in the variant name, replacing our @input expression with @LOD iteration. Middle clicking shows that indeed the first iteration will be named LOD_0. And on the graph, we can also replace the LOD number with @LOD iteration in backticks. And if we middle click, we can see it's pulling in LOD0. Great, now we can just set the for each to 3 iterations, and we have our 3 LOD variants set up once again. Instead of manually setting the for each to 3, we can also have it determine the number of loops based on the number of LOD meshes. Connect the SOP create to the second input, and change the iteration method to for each primitive in second input. This gives us an input parameter to select which primitives to include. If we copy in the path to the LOD0 mesh and replace the 0 with a star, it'll run the loop 3 times, once for each mesh. With that done, we can reconnect our geo to the network. Now let's add another variant set for the material. So I'll detach the material library so we can focus on it. You could use a variant set to change material parameters, or even switch to different materials entirely. But since this asset has several different resolutions for each texture, I'll create a variant set to switch between texture resolutions. Let's select the material library and take a look at the scene graph tree to see where the texture paths are being stored. Under the material prim, we see a prim named albedo, which is our material X image node that's pulling in the albedo texture. And in the right pane, there's an attribute called inputs file that houses the texture path. If we put down an edit material properties node and point it to the albedo prim, we can hit create parameters, which will let us alter that file attribute. But that will only set the texture for a single property for a single variant. Too manual, too many nodes, I don't like it. If we take a look at the texture files, the various resolutions are conveniently named identically apart from the resolution. This means we could use a wrangle to simply replace the resolution part of the file paths all at once. Delete the edit material properties node and put down a wrangle. To point it to the nodes we want, we can just select them in the scene graph tree and drag them into the primitives parameter. Alternatively, if you look at the prims that are pulling in the textures, you can see that the info ID attributes all start with ND image. So in the primitives parameter, you can type %shader type ND image star to target them all. Let's set the paths to something to make sure it's working. So s@inputs file equals test. In the scene graph tree, we can see that the textures are now all pointing to test. Now to replace just the resolution part of the file name, we can use the replace function, which takes the original path as the first input, the string to replace as the second input, 2048 in our case, and the string to replace it with. I'll make this one a parameter called res and set it to 4096. Now all of the file paths are pointing to the 4K textures. Let's make this into a variant set with an add variant. Connect the material library to the add variant and the block begin. Point it to /basil_big. Name the variant set, I'll go with res, and now we can hook up this wrangle a few times to set the texture paths for each resolution. And I'll name each variant by naming the wrangles. You can probably see where this is going. We're just iterating through numbers again, so we can do this in a for each instead. But first, let's investigate this warning we're getting on the add variant node. It says variant has opinions which are weaker than existing opinions, and lists the opinions we're trying to set on the texture paths. Inspecting the layer, we can see that we're defining the variants correctly. We have 4 variants, and each one is setting the various file attributes to the correct resolution. But if we change the variant, the paths don't change. They're all still in 2048. Why is that? We're running into this problem because of how USD handles opinion strength. We briefly covered LOPs in the last video as the mnemonic for the opinion priorities of the various composition arcs. L for local is the strongest. When we set the 2K paths in the material library, we set local opinions for the file attributes. B for variant is weaker, and that's what we're trying to use to override the paths. So how can we make the variant opinion override the stronger local opinion? We can't. We just need to get rid of the local opinion. There are 2 ways of doing this. Remove the opinion from the layer with Python, or simply don't set the paths in the material library. I'll go over the Python method first, as it doesn't require any other changes to our network. Connect the Python LOP in between the material library and the add variant node. If you've never used Python in LOPs or USD, this blank canvas is a bit daunting. We need to grab the texture paths, then iterate over them to remove the opinions. Thankfully, there's a handy preset to get us most of the way there. Click on this arrow and select Dim All Lights from the drop-down menu. This is using a selection pattern to grab all of the light primitives, then iterating over them to get an attribute named intensity and changing it. To grab the primitives we want, we can copy our selection pattern from the wrangle nodes. Then we can change the get attribute call to get the file attribute instead of intensity. And we don't want to set or change the value, we want to remove the opinions on it. So we can delete this line and instead say file.clear. Now our variant set can successfully switch textures because there are no opinions on the texture path before the variant is applied. We're still getting a warning on the add variant node, because the attribute inputs file still technically has an opinion. In the layer code, we see asset inputs file, which is an opinion on the existence and the type of the attribute inputs file, but since there's no opinion on its value, the variance will apply just fine, so we can ignore the warning. I prefer this method, but for completeness, let's go over the alternative. Delete the Python node, then jump into the material and simply remove all of the texture paths. Jump back up and inspect the layer to see that now we have no opinions at all on the inputs file attributes. They're gone. The problem with this is that the wrangle was previously replacing the resolution in that attribute, so now that it's unset, there's nothing to replace. Instead, we need a base path and we'll fill in the resolution from there. So let's delete this replace function and use sprintf instead. For the first argument, we'll paste in the path to a texture to use as a base and replace the resolution with %s. This is what will be replaced by the second argument, which we'll set to our res parameter. That's working, but there are two problems. Firstly, the file path is not being set as an asset path, which is indicated by @ symbols around the value. And just to confirm that, if we open up the write pane under metadata, the type name is listed as string instead of asset. This means that the output processes won't work on our texture files, so it won't relativize the paths or collect them correctly. To fix that, we can add another wrangle. Point it to the same primitives and add the line USD_add attrib. 0 for the current stage, @primPath for the current prim, inputs file for the name of the attribute we're creating, and finally asset for the attribute type. If we try to do all this in one wrangle, it won't work. The inputs file attribute has to exist as the correct type before we set it. Now if we look at the albedo path, we can see it's an asset and it's being resolved successfully. Which brings us to the second problem. If we look at the path for any of the other textures, they're all being set to albedo. We can fix that by replacing albedo in the path with %s again and replacing it with @primname. Now they should all resolve except for normals. This is because the normals texture is named normal OpenGL, so if we rename the image node to that, it should work. With that all finally done, rather than apply these changes to each variant branch, let's delete the rest of them, wrap this in a for each loop, and just like last time, we can delete the variant block and uncheck create options block. Now on the for each end, change the iteration method to for each string in parameter. This gives us a string parameter where we can specify a space-separated list of strings to iterate over. We have 2, 4, 8, and 16K textures, so we'll put in 2048, 4096, 8192, and 16384. This will cause the loop to run 4 times, with iteration value set to one of the resolution values each time. To make it clearer, I'll prefix each of these with res. So now we can use res iteration value in the loop to access the resolution. So on our wrangle, we'll set our res parameter to @res iteration value in backticks, and we'll set the name of the variance to the variant set name underscore @res iteration value in backticks. Now we can double check that's all set up properly by selecting the for each end node and inspecting the layer in the layers panel. You can see that we're prepending the variant set res, and then we have 4 variants, one for each resolution that sets the texture paths to the appropriate resolution. And we can test it by switching the res variant and seeing that the paths do indeed switch to the correct resolution. Success! Let's hook this back up to the network. Now, I'm sure you're thinking, that's great, but can we make it even more complicated? Yes, we can. Let's set up a nested variant set. First, let's make it clearer what we've done so far by renaming our variant and loop nodes. Res variant set, for each res end, for each res begin, LOD variant set, for each LOD end, and for each LOD begin. Oh, and this wrangle should be called set res. Jumping into the SOP create, if we bypass the blast and jump back up, you can see that there are multiple versions of the Bazel plant in addition to the LODs. Let's make our lives a bit easier by standardizing these mesh names. The first model variants have no number on the end, so we can add that in with a restructure scene graph set to rename. We'll target everything that ends with _OL and append an _000. And now that we've changed those paths, we'll need to also update the paths in our graph proxy, graph render, and for each LOD. If I lay all these meshes out like this, you can see that we have 6 model variants, 3 LODs, and the proxy meshes. We've already made an asset out of the first model variant, where we can switch between LOD variants using a LOD variant set. But in doing so, we've set opinions on the render and proxy mesh. Since we can't override those, how can we add another variant set to switch between model variants? There are quite a few ways, but here's the simplest. Each model variant will contain the definition of the entire component for that model, including the LOD variants. Let's demonstrate with the first one before we move on to setting up a loop for the rest. Put down an add variant to new primitive, set the primitive path to /basil_big, the kind to component, and we can leave the variant set name as model. As you can see in the scene graph tree, this has created a component prim for us. Now connect our geo network to the multi-input and set the variant source primitive to /basil_big. This is the path to the tree from the multi-input that we want to place over the primitive path for each variant. And for now, let's set the variant name to model_0. If we toggle the Set Variant Selection button, our basil plant disappears from both the viewport and the tree. Let's see what's going on in the layer panel. We define our component prim, add the model variant set, and everything else is defined under the variant model_0, including the proxy mesh and all of the LOD variants. Cool. So now let's iterate through the model variants with a for loop. I'll call it for each model, and since we're essentially defining a whole component in each loop, we don't need a layer break, so we can delete the begin node. I know it feels a bit strange having a loop with no begin, but it'll be okay. You'll get used to it. Let's put this after the add variant, but connected to the third input. And for clarity, let's change the color so we can more easily distinguish between the model and LOD loops. Then, like with the other loops, I'll prefix the iteration variables with model. To set the number of iterations, connect the restructure to the second input, and then set the iteration method to for each primitive in second input. Now we can choose the prims to iterate over. I can copy the path to any mesh, and simply replace the numbers at the end with an asterisk. This will run the loop 6 times, once for each model variant. Since all of the meshes are numbered, we can use the model iteration variable to drive the values. Starting with the add variant node, on the variant name, replace the 0 with @model_iteration in backticks. Then on the graph render, replace the variant number with @model_iteration in backticks. But since the model numbers are 3 digits, we need to put this inside of a pad0 function and set the pad to 3 digits. Let's copy this and do the same for the proxy mesh. Now that's pulling in the correct proxy and render meshes for each LOD and each model, and storing them in a model variant with the model number. Done. We can't see anything because we haven't set a variant yet. Let's do that by selecting the for each node, and then in the scene graph tree, right-click on the component and select a model variant. That creates a set variant for us, and we can see our asset. And if we right-click in the viewport, we can now switch both the model and LOD variants on a single component prim. Super cool. I'll set it to model0 LOD0, so those will be the defaults whenever the asset is referenced in. Now we're not quite done with this yet, as now that the model can change, so too can the bounding box, meaning that the current static loft payload info approach isn't going to cut it. Instead, we need to add a separate loft payload info per variant in the model variant set. Another trusty for each loop can help us do just that. Set it to iterate over variants in the first input, and set the variant set to model. This will iterate once for each model variant, and we can access the variant name in each iteration with the iteration value variable. So in each loop we need to set the variant to the current model. Then we run the loft payload info to get the info for that model variant. Next we need to store that info somewhere, so I'll put down an add variant, point both paths to /basil_big, and set the type to component. We'll store the payload info into the model variant set under the name of the matching variant with @iteration value in backticks, and uncheck set variant selection, as we only want the variant to contain opinions from the lofted info. Let's select the for each node and check the layer code to see what's happening. We've got our xform component prim, we add our model variant set, and then for each variant we get the lofted kind and extents hints. We're also getting a redundant opinion on the variant. This is coming from the set variant node, so all we need to do is put down a layer break after it to stop that coming through. Now if we unload the payload, which I'll preview with a configure stage, we can still switch variants, and the bounding box will be updated accordingly. You'll notice that in this state, we don't get a list of the LOD or res variants. Since this loop is only telling our payload layer about the model variant set, it doesn't know they exist. Now, that's not necessarily a problem, so I'll leave it to you as homework to figure out how to add that if you want. As a hint, here's what needs to be added to the payload layer to make them appear. Bonus Houdini points if you can do all 3 variant sets with just 2 loops. Anyway, that's our variant sets all done. We can now move on to the last composition arc of the video, inherits. I won't get too deep into the details on the usage of inherits here. If I get around to making a video on the specializers composition arc, I'll go into it then. The high-level overview is that inherits allow you to broadcast overrides to prims in your scene. For example, here we have a bunch of assets all inheriting from the primitive class/pig. If I add a sphere under that primitive, it shows up in all of the inheriting primitives as well. Going back to our asset, we actually already have an inherit applied without us even knowing. If we take a look at the material, by default, it's setting up an inherit from the path class material/material name. So if we had a scene with a bunch of Basil assets, we could override all of their materials at once by defining a new material at that path. Setting up inheritance for our component is also super simple. Add a primitive node to make our class prim. I'll call it class/basil_big and set the specifier to class and everything else to none. Now put down a reference, point it to our component, and set it to inherit from first input, and we'll inherit from the class prim. Inspecting the layer shows that we've indeed added an inherit pointing to the class prim. Great. If we check back in on our Basil patch, we can now override anything on or under our component. For example, we can globally set the variant, add new meshes, and even override the existing mesh. And with that, we've finally finished our asset. So let's hit save and double check what we've exported. We have the material layer containing the material and its assignment, with variants for each of the texture resolutions, which have been conveniently saved in this text folder. We have the geo layer containing all of the model variants and LODs, we have the payload layer that references those two layers in, and we have the main asset layer that inherits from a class prim, payloads in the payload layer, and contains all of the payload info needed to properly represent the asset, even if the payload is unloaded. One last thing we can do is look at how to get this into the layout asset gallery, so we can have easy access to it whenever we want to pull it into a scene. Click the new Pane tab button, and under Solaris select Layout Asset Gallery. Here we can drag assets into our scene. If we want to add our Bazel asset, we first make a new asset database. I'll just call it temp. Then, we can click the Add Asset Directory button and point it to the asset folder. Houdini will render a thumbnail and add it in there for us. I don't like that thumbnail though, so remove it from the asset gallery, and let's render our own. Start by sublayering in the Bazel asset. The component builder has a super handy thumbnail camera, so I'll jump in and steal that. I'll make sure it's activated, and set these variables to 0, so we don't have to worry about adding the parameters. Then point it to our component, and look through the camera. And we have our asset nicely framed based on its bounding box. Next, I'll hook up the lights we used earlier, and now we can put down a karma node, set the camera to our thumbnail camera, set the resolution to 128 by 128, I'll use XPU, and we want to render into our asset folder and name it bazel_big_thumbnail.png. Though if you're in ACES CG color space, then you'll need to apply the display view transform. Under Advanced Sampling, set OCIO transform to display view. The default should be the sRGB display with ACES SDR view. I don't think this option was always there, so for completeness, here's the long way to do ACES conversions. Change from PNG to EXR, and hit render. Then, in the terminal, you can convert it to an sRGB PNG using this command, which uses the OpenImageIO tools binary that ships with Houdini. And I can delete the EXR now, as we don't need it. Now add the asset back in, and it should pick up our custom thumbnail instead. If you want variants of the asset to appear in the gallery, then you'll need to use a USD file and thumbnail per variant. The docs for the asset gallery cover how to set this up, but in summary, you just need to put all of these into a subfolder named variants, with one USD layer per variant and a PNG file for each with the suffix of _thumbnail. Exporting the variant layers is pretty simple. Sublayer the asset again, and run it through a for each loop set to iterate over variants in the first input, setting the prim to /bazel_big and variant sets to model, as I don't want a separate asset entry per LOD. That'd be overkill. Now set combine iterations to separate layers. In the loop, all we need to do is reference in the asset, then use a set variant node to set the model variant to the current iteration value, and put down a configure layer node to set the file name, bazel_big_at_iterationvalue.usd, and I'll make it an ASCII format. Check the layers panel, and we have one layer per variant, with each layer only containing an opinion on the model variant, with the save path set to the asset name _variant name. Put down a USD ROP, save it into the variants folder, and I'll just call it temp.usd, as we don't need the root layer. Set the save style to separate layers, as we don't want to flatten all of our variant layers into one USD. Then, to get all of our layers to save into the same place, add the output processor to save all the layers to the same folder. Now hit export and check the variants folder to see all of our variant layers. We can delete the temp.usd. To render thumbnails for each of these, we can use tops and run them through our existing thumbnail render setup. Put down a top network and dive inside. We'll use a file pattern top to grab all the USD files in the variants folder. That gives us attributes for directory, file name, and extension for each one. Jump back up to the stage and use these attributes to set the path on the sublayer. That way, each work item will pull in a different variant. We'll also use the attributes in the output, saving to @directory/@filename _thumbnail.exr. Now jump back into our topnet and put down a ROP fetch pointing to the render ROP. If we generate the work items, we can see that the ROP fetch says the expected outputs are USD files. Since the USD render ROP first exports a USD file and then uses Husk to render the images, the ROP fetch can't tell what the output files will be. We can fix this by copying the output path parameter into the override output image on the render ROP. Then, on the ROP fetch, under output, set the output palm name to output image to point it to that override palm. Generate again, and now the expected output is our thumbnail. For those playing along in ACES land, we then append an OpenImageIO top. This will take the upstream EXR files as input, and we'll set the output using our file variables again. So @directory/@filename _thumbnail.png. Under image processing, we want to do a color transform, with display set to sRGB display, and view set to ACES 1.0 SDR video. That will convert the ACES CG EXRs to sRGB PNGs. And then after that, we can delete the EXR files using a file remove and pointing it to the EXRs, either by using the file attributes or by referencing the output path. Before we run this, I'll set the scheduler to 1 CPU so that we don't try and render all of the thumbnails at once. Now let's run it and see what happens. The EXRs get rendered, converted to sRGB PNGs, and then the EXRs get deleted. Done. Now we can point the asset gallery to our asset folder again, and this time it'll pull in all of the model variants and their thumbnails. All done! I hope that wasn't too overwhelming for anyone. I initially planned this video to be a really quick follow-up to LOPs for solo artists, to cover the composition arcs I didn't get a chance to cover. But there was so much to talk about to do justice to the topic of asset creation that it became another almost hour-long video. And I didn't even get to fully cover inherits or specializers. I do want to say that all of these features I've covered are just conventions. You don't need to implement any of them if you don't need them in your workflow. If all you want to do is save a mesh with its material, then just do that and call it a day. That said, the component builder nodes will implement pretty much all of this for you. So if any of these features sound like something you might want to use in future, then I highly recommend exporting your assets through those. They really do make asset creation much simpler. I'm just a big fan of reinventing the wheel for the sake of learning and having complete control. And hopefully now you're an expert in building components, so if you do go back into the component builder workflow, you'll at least know what they're doing and why. Now, go build some cool assets.